Welcome everyone to the next seminar on probability stochastic process from IME-USP. And today we have with us Tertuliano Franco from Federal University of Bahia. And welcome Tertuliano, and thank you very much for accepting the invitation.
Thank you, Aline, for the invitation. I'm very glad to be here at the USP seminar. I'm going to speak today about the following topic: is the slow bond run walk and the snapping out Brownian motion. Okay, thank you very much for the invitation, and let's start. This talk is based on the joint work with Silva, my former PhD student, and my colleague Dirk Erhard, which this work has been published in Annals of Applied Probability in this year. Let me full screen. Yeah. So, but what is a slow bond? Let's start discussing what is a slow bond. Some literature. Particle systems with a slow bond or many slow bonds have been studied a lot in the last decade. Mainly the SEP, but also the zero range process, a little bit on the KMP. By now, we have already many authors, myself, Patrícia Gonçalves, Claudio Landim, Adriana Neumann, Rangel, Otávio Menezes, Milton, Bernardin, Cedric Bernardin, Tavares. Tavares is my former PhD student, also Mariana, Dirk, Erhard, Errinu, Nahum, Frometa, Misturin, Derrida, Sadhu, Hirschberg, among many others. I'm for sure I'm forgetting some people. A lot of people here. For instance, I forgot here Simas, Valentin also. They have related works. So there is a big literature on these talks, on slow bonds, on the role of slow bonds in particle systems. How a slow bond affects the microscopic behavior of a particle system. But what is slow bond in a symmetric context? In an asymmetric context, the definition would be different. Okay, the definition is the symmetric context. So let's see probably the most standard case, the symmetric simple exclusion with a slow bond. Okay, so we have in the exclusion process, we have at most one particle per site. So let's say the black ball is occupied and white ball is empty. So each edge, each bond has a Poisson process associated to. When this Poisson process rings, we exchange the value. So when this clock rings, this black ball, for instance, would go to here. Okay, so this is the movement in the exclusion process. In words, the exclusion process is a bunch of run walks with this additional rule that two run walks cannot occupy the same site. So a slow bond, the slow bond is this special bond here in green. I'm not sure if you can see, but it's this special. We have a special bond here, which has a smaller rate. This Poisson clock rings much less. So this you see this above alpha is positive real number, beta is non-negative, and n is the scaling parameter, which could be, for instance, the size of the system. Let's think about it. Let's say the box with n sites. Okay, and these systems are usually scaling the diffusive scaling. So the space is divided by n, and the time is scaled by n squared. Okay, so you see, since alpha is positive and beta is non-negative, this rate goes to 0 as n goes to infinity.
Sorry, Tertuliano. This beta, it's above n, right? It's a little bit small. I'm a little bit blind.
Alpha and beta are fixed. Are two fixed real numbers.
Is in the exponent of n, right?
Yeah. It's in the exponent of n.
Yeah, it's just because it's a little bit small.
Yeah, that's the problem of not using Beamer. My letters are not so beautiful. So thank you very much. This is n to the power beta. Not much. Let me Okay, this is too small, I think. Okay, is the power of n. Okay, so this rate is going to 0. It's not only smaller than the other rates, it's going to 0 as we increase the scaling parameter n. Okay, that's the slow bond. And the point here in all these works, the phenomena here is that there is a phase transition a dynamical phase transition, always. For beta equal to 1. Okay, that's the big feature of this low bond. The system has some behavior for beta smaller than 1, has another behavior for beta bigger than 1, has this critical behavior for beta equal to 1. Okay. I can give you an intuition of that, but I don't have much time, so maybe at the end I can explain why this happens. But that's the point. In all these works, there is a phase transition for this special value of beta. And then when starting with the advising activity with Diogo, Dirk and myself, we noticed that despite there are so many works in particle systems for the slow bonds, for the effects of a slow bond, we could find in the literature any result about the convergence of the random walk with a slow bond, which is the most simple case. You can think, what's the random walk? Is the exclusion process with a single particle. So in certain sense, it's a sub case of the exclusion process. But you couldn't find in the literature the limit for the random walk. And by limit, I mean the central limit theorem. Invariance principle, this kind of thing. The fluctuations, the central limit theorem for the random walk on this media, where there is this small rate to cross this special bond. Okay, so let's define more precisely what is the slow bond random walk. Okay, up to now, some question? You can write in the chat if you want also. Any question about the...
I just to be sure, it's not a question, but this is slow bound. Actually, it's there. It's not something that like you change your particles and then you become slow, right? It's there since the beginning.
Since the beginning. Keep in mind that for each n, we have a different particle system. The particle system is being rescaled. So for each n, we have a different system. Okay, the size of the system is increasing. So we are considering, for instance, the box with n sides. So the size of the system is changing. The time at which you are looking for the system is also being scaled. And the value of this slow bond is being scaled. It's going to 0.
But the place where this is slow bond it's fixed.
It's fixed.
Yeah, this is my question. So it's there and you don't change.
It's there forever. Yeah. It's going to be clear in the next slide. Thank you, Aline. Okay, so let's define precisely what is the slow bond random walk. So definition. The slow bond random walk. Okay. Slow bond random walk, which is this green. You see the answer to your question. The slow bond is always close to the origin. It's a fixed position. Thank you, Aline. The slow bond random walk is the continuous time Markov process. So it's a random walk, but we're looking at continuous time, not at the discrete time. Okay, so we're going to denote it by xt slow on z. Whose generator acts on local functions from z to r. As you can see the rates here. The generator is just a way to define the process, but you can think about this Poisson clocks. It's the same. See, the Poisson clocks are here. Oh, sorry. Are here. You see the values, the parameter of the Poisson clocks are here. So you see all parameters are 1/2, except these two Poisson clocks, which is to jump from -1 to 0 and to jump from 0 to -1. Aside of these two rates, all the rates are 1/2. Okay, it's a run walk on Z with this, and the rate at which it can it tries the run walk tries to jump from 0 to -1 and -1 to 0 is given by this alpha divided by 2 n to the beta. It's too small. You can see it's alpha divided by 2 times n to the power beta. Okay. Okay, that's the definition of this low bound run walk. You can see is as n goes increases, it's harder harder and harder to cross the orange. So the question is, which is the limit for this run walk? Okay, so the first main result of our work with Dirk and Joe is the following. So consider this low bound run walk in the following scaling. We are dividing it by n and look it at time tn squared. But it's the same as the usual, if you remember of the Donsker theorem, it's the same scaling. But in the Donsker theorem, usually one does the following, but it's the same. Okay, take the time tn and divide the space by square root of n. Is the same, just change n by n squared. I look at this. We choose this form just for convenience of notation, but it's the same. Okay, it's the same. The usual scaling towards the central limit theorem for the run walk, for the functional central limit theorem. Okay, is that clear? This tn squared here is the divided by n is the same as tn divided by square root of n. Okay, consider the rescaled slow bound run walk, where this is the walk starts from un, where u is a real number, not 0, and this is integer part of un, so it's macroscopically close to u. Then the sequence converges in distribution with respect to the J1 score-Hawley topology of D. We need D here because the process is continuous, okay? We didn't interpolate, so the particle goes to here and stays here for some time, then jumps to the next point for one of its neighbors. So the process had lag. So we need to work on D. So it converges the process YT, where YT is the following. If beta is between 0 and 1, it's the usual Brownian motion. The Brownian motion BT. It means the rate is going to 0, but it's not enough to make any difference in the limit. It's the same limit as if the slow bond was there. If beta let's go. If beta is 1, the limit is as the title says, is the snapping out Brownian motion, which you denote S SNOB T. Okay, I'm going to explain in a moment what does it mean. Okay, and if beta is bigger than 1, as expected, the limit for the process is the reflected Brownian motion, reflected at 0, B reflect T. Okay, is that clear? So for beta smaller than 1, the slow bond plays no role. For beta bigger than 1, the strength of the slow bond is so big that it completely divides the space in two in the limit. And if beta is 1, then the limit is this snapping out Brownian motion. Okay? So in the next slide, let's discuss what is this snapping out Brownian motion. Okay? Any question by now? It's clear that the statement is the usual Donsker theorem. Okay, for the functional central limit theorem, or we're doing a central limit theorem for the trajectory, for the whole trajectory. Okay, and this limit is the usual Brownian motion for beta smaller than 1, is the reflected Brownian motion for beta bigger than 1, and this is a special process. This is snapping out Brownian motion. It's a Brownian type process. Okay, so stop me if you want. Okay, so but what is the snapping out Brownian motion? So the reflected Brownian motion needs no explanation. This is the it's the Brownian motion when we touch 0, we are reflected to the same half line, and the absorbed Brownian motion is the Brownian motion which, when it hits 0, stays at 0 forever. Okay. So before I explain what is the snapping out Brownian motion, let's see what is this elastic Brownian motion. It's a classical Brownian type process, but it's not so known. So, okay, what's this elastic Brownian motion? The elastic Brownian motion is a middle term between being reflected and absorbed. So we toss z. Z is this random variable of exponentially distributed, okay, with a parameter kappa, which is independent of the reflected Brownian motion. Okay. So what is the elastic Brownian motion? We follow the reflected Brownian motion. We follow this process. Okay, we follow this process until the moment the local time of the reflected Brownian motion reaches this value z. At this point, the process is absorbed. So the elastic Brownian motion is absorbed after the absorbed Brownian motion, but of course before the reflected Brownian motion, because the reflected Brownian motion is never absorbed. It's a kind of interpolation between being reflected and absorbed. Okay, it's a classical.
In this case, you'll be absorbed by 0 also, because
because going to be absorbed at 0, because the local time is the local time. Look at 0. So the moment the local time reaches this value z, you are at 0. So you are absorbed there. Okay. The local time of the Brownian motion is intuitively is the time the Brownian motion spends there. Of course, the time the Brownian motion stays at 0 has 0 Lebesgue measure, but it has a density. Yeah, if you define, just to recall what's the local time, you can find the local time in many ways with from stochastic calculus, with Tanaka formula, but you can define it like that. You can define this mu t. If A is a Borel set, you can define it like it is the time the Brownian motion stays over A. And this can prove that this process has a density with respect to Lebesgue measure. Okay, and this guy has a continuous version in time and space. Okay, I'm going to enter. I'm not going to enter into details, but it's the classical local time of Brownian motion. Okay, this more or less the time the Brownian motion stays there. The idea. So what is the SNOB? The SNOB is a very recent process constructed by Antoine Lejay in 2016, also in the same journal, Ones of Applied Probability, which can be defined as follows. So the state space of the SNOB is not R, it's not the real line, is this set G, which is minus infinity to 0 minus, united to 0 plus, to plus infinity. Okay, so we cut the real line in two pieces and close the state spaces are two closed half lines. Okay, and the definition of the SNOB, one phrase, is the following: we follow the k-elastic Brownian motion. Okay, sorry, a kappa. This is a kappa. Okay, so we follow the kappa elastic Brownian motion, and once the kappa elastic Brownian motion is absorbed, we restart the process on the opposite half line. Is that clear? So is the elastic Brownian motion. We start in the saying the positive half line. In this, we start here, let's say. We follow the elastic Brownian motion. So at some time, the process is absorbed at 0 plus in this case. In this moment, we restart the process, but now in 0 minus. Okay, that's the definition of the snapping out Brownian motion. It escapes from one half line to another half line. It is constructed by gluing pieces of the elastic Brownian motion. Okay, this has been constructed by Lejay. Yeah. Any question about the definition of the SNOB? Is that clear? Okay, so if not, and one of the main results of Lejay in this paper is the following. He gives an explicit formula for the semigroup of this Brownian type process. Okay, he has this formula which involves the local time of the Brownian motion. So by semigroup, I mean the expectation of a function of the process at some time. So Pt of f x. Understand in the sense. For any process, the semigroup is the expectation of a function of the process start from x at time t. Okay, so he gives this formula for the semigroup. In our work with Diogo and Dirk, we provide another formula, more explicit, really giving integrals. Not here you have the local time and the Brownian motion. Okay, it's known that the joint distribution, but it's a lot of work to deduce it. But we're going to use it in this talk just for this formula, which has been provided by Lejay. Okay, so notice I have the kappa here. The kappa is the parameter of the Poisson. We have the local time here, and I have a lot of the modulus of the Brownian motion, and I have also the sine function, which is +1 in the positive half line and -1 in the negative half line. Okay, and Bt is the usual Brownian motion. Okay, this formula it's based on this formula. We are going to show the converse of the process. Okay, so next, let's state the second main result of our paper with Dirk and Diogo. So, okay, we have defined so far the slow bond run walk and the snapping out Brownian motion. Okay, so the second main result of our paper is given by Berry-Esseen estimates. by Berry-Esseen estimates, we mean estimates on the speed of convergence for the central limit theorem. Here for fixed time, not for the whole trajectory, but for you choose time t, and you can say which the for a given t, which the distance in some distance which meteorizes the weak convergence. Okay, the central limit theorem is for weak convergence. So, and the weak convergence can be meteorized in many ways. There are many different ways to meteorize the weak convergence, and we were able to provide these estimates on the dual bound Lipschitz metric. Let me explain. So SD is a Polish space. In our case, it's OR or R or G. G is that guy with two close half lines. FL is the supremum. It's like the Lipschitz coefficient. You see, it's like Lipschitz. You have the distance, but you divide by distance between U and V. Okay, and this is not a norm. It's just a semi-norm. Okay, because you have to, if you take F constant, this is 0, but F would be 0. So, which is actually a norm is this guy. We add the F infinity norm with this semi-norm BL. This is a norm. This is so-called the bounded Lipschitz norm. Okay, and DBL is a metric between probability measures. Okay, it's supremum over F this BL. BLS is the set of all functions with finite. Sorry, here's just L. Okay, BLS is the set of functions of finite bound Lipschitz norm, and this is a metric for the weak convergence. It's usually called the dual bounded Lipschitz norm. Lipschitz metric. Okay. So the second main result of our paper is the following: fixed t. This is for fixed t. Okay, it's not for the whole trajectory. So mu is low Tn is the measure induced on R or on G. Okay, so it depends. You can embed the set Z both in R or in G, on G. Okay, so it's the metric induced on the metric space, which can be R or G. Let mu t is the measure induced by the Brownian motion. Okay, so it's the Gaussian with variance t. So let mu t SNOB be the measure on G induced by the snapping out Brownian motion, and let mu t half the measure induced by reflected Brownian motion. Okay, and all Brownian motions here start from U. U is the U not 0. Sorry, on U. Okay, then if beta is between 0 and 1, the distance between the distribution of this slow bound one walk and the mu t, the distribution of the Brownian motion at time t, which is Gaussian, is less than this symbol here. It means bounded by a constant times. Okay, this is more a constant times the function. Okay, where the constant does not depend neither on n or beta. Okay, so it's bounded by constant times n to the beta minus 1. If beta is equal to 1 for any delta positive, the distance between these two distributions is more than 1 to the power minus 1/2 plus delta. And if beta is bigger than 1, the distance is bounded by the maximum of n to minus 1 and n to the power beta minus 1. And you can see here some symmetry here. Because if beta is smaller than 1, this guy actually is the same as n to the power beta minus 1. Okay, because 1 over n is for sure smaller than n to the power beta minus 1, asymptotically. Okay, so we have some symmetry here. And let's just give some intuitions of why we have these estimates, which we believe to be sharp. We really believe these rates are sharp. In fact, actually, we are very close to the proof that they are sharp, but that's not. We haven't written that, so it's just an intuition. So, okay, first of all, the usual Berry-Esseen rate of convergence is n to the minus 1. Okay, if you use the same scaling of Billings, for instance, the usual like that, the rate is n to the minus 1/2. Okay, sorry. No, yeah, that's correct. But since you write like that, the rate turns to be minus 1. It's the same, okay? But in the usual textbooks, you are going to find this speed, because they use this formulation. But since you use this formulation, the usual rate is minus 1, n to the power 1 over n. Okay, so this is the usual rate of convergence in the central limit theorem towards the run walk. Okay. So for beta between 0 and 1, the limit is the usual Brownian motion, but you have this low bound. That's why the convergence is lower. You see this beta, this n to the power beta minus 1 is the rate is smaller, is not fast as the usual Brownian motion. You run walk towards the Brownian motion. Okay, so here the limit is Brownian motion, but this low bound makes life harder. Okay. For beta equal to 1, is the most interesting point here. We are going to see that the invariance principle for the local time is important in the proof. So, and it's known that the invariance principle for the local times of the run walk converges to the local time of the Brownian motion. This takes place in the usual scaling by, okay, if you consider this, the rate for the convergence of local times of run walks to local times of Brownian motion, the rate is 1 to minus 1/4. So, but since we are working on this formulation, the speed turns to be 1/2, which is this 1/2 here. Okay, and for beta bigger than 1, the problem is, the intuition is, the limit is the reflected Brownian motion, but you always have this probability. We start here, some close to microscopic point u, but we have a small probability of being trapped in the wrong half side. We start in the positive half line. The limit is the reflected Brownian motion. It means it should stay in the positive half line, but we have a very small probability of crossing the slow bond and being trapped in the wrong half line. So this is why the velocity is not so. I have this guy here. Okay, just intuition. Okay. So I don't have much time. 15 minutes, I can tell you the main ideas of the proof. Okay. Any question so far? Okay. So I have these two results. This functional central limit theorem with these three cases. Huh?
Someone just hide the hand.
Hello, Taitu.
Yeah, sure.
Hi.
I have a question. Can you go back to the last page?
Hi, Cheng, is that you? I recognize the voice.
Can you go back to the last page?
Yes, sure.
Here. So for the case beta bigger than 1, you prove that the distance is between these two maximums.
Yeah.
Is there should be n to the 1 minus beta? Because if beta bigger than 1, then that's very large.
You're right. You're completely right. This guy is, yeah. Thank you very much. Yeah, that's no, it's yeah, 1 minus beta here. Yeah, you're right.
Yeah.
Thank you very much.
Okay. Yeah. Okay, please. Thanks.
Okay, thanks, Cheng. So, and by the way, and this guy, if beta is bigger than 2, this guy is n minus 1, which is the usual rate of converge. So, in the intuition here is that if beta is bigger than 2, by some Borel-Cantelli argument, we are going to cross the slow bond only finite times. So only for finite n, you are going to cross the slow bond. Okay, you see, if beta is bigger than 2, the maximum between these two guys is n to the minus 1, which is the usual rate of convergence for the Berry-Esseen estimate. Okay, thanks. So coming back, yeah. So just a little bit on the proof structure. I'm not going to prove you anything here, but just the idea. The proof structure is the usual one: tightness plus characterization of the limit for the finite dimension margins. Okay. On tightness, you use a kind of Kolmogorov-Sentsov criterion. Kolmogorov-Sentsov criterion is in Karatza's book. Is the following words: if you control moments of the process, then it's tight. The problem is that in Karatza's book, the Kolmogorov-Sentsov criterion is stated for the space C, and here we are in the space D. So we usually have used here a version of Kolmogorov-Sentsov theorem, which is in Billingsley's book. Okay. And plus martingales. And to control the criterion here is if you control moments, the process is tight on D. This criterion is Billings, but and control moments have used the Dick martingale. Okay. And to prove characterization of the limit for finite marginals, we have used 2. Okay. The Berry estimates for a fixed time plus Markov property. In fact, plus Markov property plus some uniformicity. Okay, on the starting point. So for fixed time, you have this estimate on the distance of the distributions. Then you apply the Markov process for this finite many times, and use their estimates in each of those times. So the main point here is to prove the Berry-Esseen estimate for fixed time. And to prove the Berry-Esseen estimate, the main idea is this parity decomposition for the Forward-Fokker-Planck equation of this low bound neural walk. The name is too fancy, but for who has studied, it's very classical in Markov process. The Forward-Fokker-Planck is the derivative of the expectation of the process, which is giving if the and the derivative of this guy is the generator, the infinitesimal generator have state applied to G. Okay, so that's the main idea. So here's, you see, here you have almost the generator of the process. It's the discrete Laplacian for g, for x not being 0, neither 1, -1. Here, from 0 to 1, we have this rate, but from 0 to -1, we have this low bond. Okay, and here from 0 to -1, we have this low bond here, and here I have the usual rate. And of course, at time 0, g is equal to f. Okay, this is the Fokker-Planck equation for the slow bond run walk. And what's the parity decomposition for this guy you have created? It's the following. The system is not symmetric with respect to the origin, okay? Because the slow bond is -1, 0, okay? So the symmetry is not with respect to 0. The symmetry of the system is with respect to -1/2. Okay, so this is the symmetry with -1/2. Or if you consider the scaling, the symmetry with respect to is 1/2n minus. Okay, it's a kind of the usual notion of even function and odd function, but with respect to this guy, where is the symmetry of the system? Okay, and the lemma is this system of ODEs preserves parity. Okay, and the proof is it's very simple. The proof relies on the symmetry of rates. That's it. You see, G is defined as expectation of the function of the process. But the process, note that if you start the process on the half line, it's the same as starting the process on the negative half line and then reflect it. The law is the same. By the symmetry of the rates, starting the process, let's say, in the negative half line is the same as starting the process on the positive half line and then reflect it. The law is the same. Okay, and since the law is the same, you can prove that GT has the symmetry also. So if we start, it means that. So if we start, sorry, yeah, if we start from, so let's don't have much time. So T of x. So this is the same group, okay? dt of x of n. So then that function f, we write this as pt, the even part, of x plus, we decompose the process on the even part on the odd part. Okay, and this guy is, by this lemma, is even forever, and this guy is odd for any t. The first guy, since it's even function has the symmetry with respect to the axis. So this guy is 0. Okay, they cancel by symmetry. Do you agree? Okay, the symmetry is with respect to -1/2. So the function is equal here and here. So this guy cancels. So this guy behaves as the usual run walk. You can replace this rate here by n²/2. So the limit of this guy is the same limit of the usual run walk. And in this guy, we also have a symmetry. And this guy also have some symmetry, and with an odd function, which I have here is minus what we have here. So this guy actually is minus twice gt 0/n, And you can consider the system only on the positive half line by symmetry also. Okay, so the even part is the usual run walk. It converts to the Brownian motion. Okay, and the odd part is solution of this guy. And you see here, here we have, there is a 2 here because there was a, you see, there was 1/2 here. So twice cancels this 1/2 here. Okay, the next slide. See, so the guy's twice. And notice that this part and this part is this corresponding to the reflective run walk. Is the Kolmogorov-Fauer Planck equation for the reflective run walk. You see, is the discrete Laplacian on the positive half line, and at 0 you can only jump to 1. So the reflected parts, and here I have a potential here. So using the classical application of Feynman-Katz formula, actually is the Feynman-Katz formula. We can write the solution of this guy as this formula. As this guy. You see, this is the reflect run walk, and we have this tightening function here, exponential of the occupation at 0 of the reflect run walk. Okay, X reflect is the reflected run walk on the positive half line. Okay, this guy by symmetry, you can open the reflective run walk. You can write in terms of the usual run walk by opening the half line. So this is not reflected anymore. Okay. So now you can see you already have this guy, which is the local time of the run walk. And that's why you are going to get the local time of the Brownian motion in the limit. Do you remember at the beginning the Lejay's theorem, the expression for the snapping out Brownian motion, we have the local time of the Brownian motion. So it's almost appearing here. Here you see this minus this 1/2 here doesn't matter here. We have this n here, so 1/2 there doesn't matter. Neither this one. Okay, in the limit. So we have the limit of modulus of the run walk divided by n, which is converges to the modulus of the Brownian motion, which is the reflected Brownian motion. And here have the local time. Okay, so prove this limit. We have used this work from. It's hard to say the names. Xak, Sorgo, Foldes, and Reves. Foldes. Too many accents here in Reves. Like that in 2009. Okay, on Henri Poincaré, I think. And then based on their paper, we have proved that the expectation of 1/n 0 to Tn squared. I mean this is the local time of the usual run walk is very close in average to the local time of the Brownian motion, and this is C minus 1/2 plus delta. That's why you have that minus 1/2 plus delta in the Berry-Esseen estimates. Okay, so this is the soul of the proof. Okay, with this kind of thing, you see here you have the local time of the run walk. Okay, the local time of the run walk in 2 sites. That's why you have that 2 before. Let me go back a few slides. Many slides, actually. Yeah, the snapping out here of parameter. I forgot parameter. Kappa equal 2 alpha. And this 2 alpha comes from the fact you have 2 sites there. Sorry, people. You have -1 and 0. So you have the local time at 2 sites. That's why you have this 2 in front of the limit. Okay. So yeah, this guy converts to the local time of the Brownian motion. Then rearranging, we can recover the Lejay's formula. That's why the limit is the snapping out Brownian motion. For beta bigger than 1, since this guy converges, for beta, taking beta bigger than 1, this guy disappears. Okay, and the exponential of 0 is 1, so it gives us only the modulus of the Brownian motion. And the most technical part of the work is this part. I think I don't have much time. Okay, this guy converts to the local time of the Brownian motion. Okay, that's the idea. So we have this temptation to say that, okay, for beta smaller than 1, for beta equal to 1, it converges. So for beta smaller than 1, we are tempted to say that, okay, if for beta equal to 1, it converges. For beta smaller than 1, it should explode. But not entirely true, because you cannot, if you start from u with positive probability, you may not hit 0. So a very technical part of the work is to show that the local time of the run walk is either 0 or not too small. Okay, but I think I have talked too much, so let's stop here. Thank you very much, Aline.
Thank you, Tertuliano. Do we have any questions or comments?
Please.
I have a question.
Yes, please.
Thanks for this nice talk.
Thank you very much.
So my question is, when we prove the hydrodynamic limit, when we essentially play with a generator. So do you think for this problem, you can also kind of prove the convergence using the generator, like the martingale problem?
You say from this result to prove the hydrodynamic limit?
No.
Yeah.
Prove
or from the hydrodynamic limit.
Prove the result. Prove the result in your paper by martingale problem. Or I mean, I'm not sure if
I understand. Yeah, but the problem is the hydrodynamic limit is for many particles, for the exclusion, so I don't think so, but I have to state it carefully. If one has the limit for the run walk, yeah, with duality or with independence of, if you take for instance independent run walks, you can prove hydrodynamic limit. But from hydrodynamic limit to prove the limit for the run walk is not clear. You see that actually the hydrodynamic limit is a law of large numbers, and here we are talking about the central limit theorem. Okay. So they are different things. You see. Is that true? The central limit theorem for the particle, if you plus duality or plus, if you consider independence of particles, independent run walks, if one has, I think, let me see, yeah, if one has the central limit theorem for the one walk plus independence implies the hydrodynamic limit. But the other way around, I'm not. I don't think so. Yes, because.
I see.
Yeah. Okay. But they have much in common. That's true. In fact, the generator for the snapping out Brownian motion is very close to the PDE one obtained when proving the hydrodynamic limit for the exclusion process with a slow bond.
Ah, okay.
Yeah. So you are right in some sense. Okay. I don't think. Okay.
Can I ask another question?
For sure.
So I was working on some problem with sticky Brownian motion. So
okay, the sticky Brownian motion is a different one. Okay, you are glued to this point for more time, but they are not are not absorbed. Okay, you are not.
I was guessing like that.
Yeah.
So sorry. So I was guessing that the random walk with the slow side may convert to sticky Brownian motion. I didn't know how to prove it, but do you think the method in your paper can prove this result? Or
no, it's quite different. It's quite different. And from the beginning, our approach is strongly based. It strongly relies on knowledge of the semigroup. And I don't think that the semigroup for the sticky Brownian motion is known. I don't think so. The generator is, but the semigroup, yeah. Which know for the sticky Brownian motion is the Laplace transform of the semigroup, something like that. I'm quite sure that they know the Laplace transform of the semigroup, but there is no explicit formula for the sticky Brownian motion. People for who Cheng speak about the sticky Brownian motion. The sticky Brownian motion is the Brownian motion, but at zero it spends more time. You know, so you start here. So when at zero, the name stick is like a glue. Okay, it spends more time here. You do not spend an interval. There is no interval. You stays there, but the measure you spend at zero is bigger than the usual Brownian motion. So the behavior is different, and the semigroup is not known. I have checked. I tried to prove it, but I couldn't.
I see.
Okay, nice.
Okay, thank you very much.
Yeah, thank you too.
Anyone has any other question? I have a question, but actually you answered just in the end, because you start speaking about this elastic process, Brownian motion, and you have a kappa, which is basically give you the expectation you take to be observed, right?
Yeah, exactly.
But and then in your SNOB process, what is your kappa? Because the
kappa is 2 alpha. The parameter of the snapping out Brownian motion is 2 kappa. Sorry, it's 2 alpha.
2 alpha.
In this 2 comes from the fact we have the local time at 2 sites. Where is it? Here. Sorry, so messed up here, but if you can, yeah, you have 2 sites here. You see, have the indicator of -1 and 0, not only one site, but 2 sites. So in the limit, we are going to have 2 times the local time of Brownian motion at 0.
But it only depend on alpha.
Yeah.
What is the intuition? Because I was expecting something else. I don't know, because this is basically the time you expend to change your axis.
Yeah. But recall, it's only alpha. But in the critical case, the subcritical case is the Brownian motion. There is no alpha, neither beta. In for beta bigger than 1 is the reflect Brownian motion. There is no alpha and no beta. And for beta equal to 1, this is the exactly scaling to the local time of run walk to converge to the local time of Brownian motion?
Okay. Yeah.
Good question. Okay, so that's why alpha survives. You see, if you can show, yeah, you have when beta is 1, all this guy, it is in the right scaling to converge to the L0T.
And what you're doing now is trying to write this L as like so explicit form, right? Like a density.
We don't need to.
No, what you want to do now, this is what you were saying at the beginning, right?
Yeah, with the limits of this guy, we recover Lejay's formula. So, where is it? Sorry. Here. So we recover at the end. I couldn't give all details, but at the end we prove that the limit for the same group of the low bond run walk, the limit is exactly this guy. You see, we have exponential there. We have 2 alpha here. We have the local time. So we have the odd part and the even part of the function, but then the even part is this guy, and the odd part is this guy. So rearranging terms, we obtain exactly this form.
Okay.
In the limit.
Nice. Very nice.
Okay. Thank you.
Thank you. Very nice presentation.
Very much. Okay. Thank you for the nice invitation. I was very glad to talk to the USP seminar.
If we don't have any other questions or comments, let's thank Tertuliano. Thank you, Tertuliano. Very nice.
Okay.